In this video, we're going to work some example problems on even and odd functions and just equation symmetry. Okay, let's get started. Determine whether the equation is symmetric with respect to the x-axis, y-axis, origin, or none of these. Okay, so we're starting out, when we went through the textbook section, we start out just discussing the idea of symmetry. And not necessarily with a function, but with any equation, function or not. That's the main idea. It's a graph or an equation, function or not, can have a certain symmetry. There are three different forms of symmetry. Symmetry about the y-axis, symmetry about the x-axis, or symmetry about the origin. Or you could potentially be symmetric with respect to multiple of those three at the same time. And so we started by just studying general equations, looking for those three forms of symmetry. And then from there, we went more specifically to functions, which is just a specific type of equation, right? And talked about those forms of symmetry related to functions. And the name even and odd function is just a name for a function that has, the even function has symmetry about the y-axis, the odd function has symmetry about the origin. Based on the definition of a function, there is no symmetry of a function about the x-axis, except for the trivial case of f of x is equal to 0. Right, a function, you can't have symmetry about the x-axis because a function can't have, to have symmetry about the x-axis, you have to have two or more y values at the same x point. That's not a function then. Okay, so we're going to start out with example problems, not talking about functions. We're just going to look at general equations. I mean, this happens to be a function, but we're just thinking about general equations, and we're going to test for the three possible forms of symmetry. That's it, because again, note, because this can be confusing, even and odd functions have, it's the same thing as, it's all these symmetry tests. All of this boils down to these tests for these forms of symmetry. It's just with even and odd functions, they're given this name, even and odd. Even just means it's a function that's symmetric about the y-axis. Odd just means it's a function that's symmetric about the origin. That's it. So how do we test for these three forms of symmetry? These are the three possible forms of symmetry, at least for an equation in two variables. We talked about how you could extend these concepts to equations with more than two variables, but perhaps with more than two variables, there's more forms of symmetry as well, but that's beyond the scope of this course. So we're focusing on equations in two variables, and these are the three forms of symmetry. How do we test for these? Well, you can think about the concept of the transformations of graphs that we talked about in the previous section. If you want to flip a graph or mirror a graph about an axis, you replace the opposite variable or variables, if there's multiple variables in the equation, with the minus of that variable. That's how you can flip an equation about a certain axis. Well, the idea is if we do apply that flip, we simplify and we get the original equation back, then that equation is symmetrical about that axis because we flipped it and nothing changed. You see? So if we want to test if this equation, or you can think about graph, you can think about it both ways, is symmetrical with respect to the x-axis, what do? Well, let's flip this equation with respect to the x-axis. So we replace y with minus y, or just put a minus, we'll do like that. Okay? Now we've flipped it with respect to the x-axis, right? So let's simplify. That's not the same equation. So this is not symmetrical with respect to the x-axis. What about the y-axis? Well, let's flip this equation. Let's apply the transformation and flip this equation with respect to the y-axis. Replace x with minus x. Simplify. Okay, we get the original equation. So this is symmetrical with respect to the y-axis. Right? If you think about whatever this graph looks like, if you flip that graph with respect to the y-axis, nothing changes. That's the idea. Okay, now let's check to see if it's symmetric about the origin. How do we check to see if it's symmetric about the origin? You flip it about the x and the y-axis. So you put minuses in front of both variables and see if you get the original equation. So No. So this is only symmetrical. This equation is only symmetrical with respect to the y-axis. Okay, let's check if this is symmetric with respect to the x-axis. We replace y with minus y. Okay. So the absolute value of minus y is just y. That is just the absolute value of y. Okay, that's the same equation. So this is symmetric with respect to the x-axis. What about the y-axis? Okay, so no, that's not the same equation. Okay, what about the origin? No. So this is only symmetric with respect to the x-axis. Okay, let's check the symmetry with respect to the x-axis. So replace y with minus y. So, oh no, this is plus. Yes, it's symmetric with respect to the x-axis. What about the y-axis? Yes, symmetric with respect to the y-axis. What about the origin? Yes, so it's symmetric with respect to all three, x-axis, y-axis, and origin. This is a circle. The idea is, so we talked about this in the previous video, this is kind of confusing because you might be thinking, well, okay, well, if something is symmetric with respect to the origin, then it must be also symmetric with respect to the x and y axis, right? No, not necessarily. The only thing is, and I'm not sure if this is officially true, but a mathematician can comment on this, but it should be true, is that if something is symmetric with respect to if you find that something is symmetric with respect to the x and y axis, then it also is going to, as a result, have to be symmetric with respect to the origin as well. So once we determined these were yes, then I don't think I needed to do this. We already knew, once these were a yes, we knew this was going to be a yes. And so it's like, okay, if you're graphically, if you're symmetric with respect to the x-axis, okay, so one way of looking at it is if you flip the graph about the x-axis, the graph doesn't change. That's one way of looking at it. And from an equation standpoint, we know from the transformations of graphs section, we know how to flip about an axis. So we replace y with minus y to flip about the x-axis. The equation doesn't change. That's the same idea. But you can also look at it going from point to point. If this is a point xy, if you go to minus y, okay, you're on the graph. Like you don't, like maybe there's not a graph down here. So when you go to minus y, there's no graph. But okay, so I mean, if all you did was go from y to minus y, the x didn't change. That's the idea for the entire graph. If you go from y to minus y, you're on the graph. You're still you're still on the graph. Or if you're down here, if you start at x minus y, if you start down here, if you multiply y by minus 1, you go to xy, you're on the graph. That's not the case if we go from, if we're here, we're at, let's say this is xy, and we go to minus xy, we come over here, we're not on the graph anymore. You see? Now, symmetric with respect to the y-axis, okay, it's the same idea, just for the y-axis. I mean, it's everything we just talked about, but it applies to the y-axis. If you flip about the y-axis, the graph doesn't change. So in that case, in the equation, if you replace x with minus x and simplify, you get the same equation back. And then, but if you do x, no, if you take any point and multiply the x by minus 1 and don't change the y, you go from xy to, I mean, that's the idea. You take any point, xy, you multiply the x by minus 1, don't change the y, you're always going to be still in the graph. Okay? Now, for symmetric about the origin, let's look at a case where you're symmetric about the origin, but you're not symmetric about the x or y axis. Okay? So, what this is saying is that if you have any point, x, y, it could be minus x, whatever, any point, if you multiply both x and y by minus 1, you'll be on the graph. So, you multiply, this is x, y, you multiply y by minus 1, come here. You're not on the graph, though. It's not symmetrical with respect to the x-axis. But you multiply, from there, you multiply x by minus 1, now you're on the graph. You see? So it's symmetrical with respect to the origin. But if you have a circle, okay, so you take any point, I mean, we'll start down here, minus x minus y. So if you multiply the y by minus 1, you go to minus x, y, you're on the graph. And that's the case for every point. So it's symmetric with respect to the x-axis. Now, if you multiply, from there, you multiply x by minus 1, you're on the graph as well. So it's symmetric with respect to the y-axis as well, and it's symmetric with respect to the origin. But you see what I mean? How if you're symmetric with respect to the x and y-axis, you have to be symmetric with respect to the origin, I would think. It's not an official math statement, because if you're symmetric with respect to the x-axis, then if you multiply y by minus 1, you're on the graph. But then if you're symmetric with respect to the y-axis, then if you multiply x by minus 1, you're still in the graph. But that's the definition of symmetric with respect to the origin. If you flip about both, you're on the graph. So anyway, yeah, that's the idea. Okay, let's check symmetry with respect to the x-axis. So replace y with minus 1. That is not the same equation. Okay, let's check symmetry with respect to the y-axis. So let's replace x with minus x. That is not the same equation. Okay, now let's check symmetry with respect to the origin. So, and again, so the graph where we did this, if we check the equation for this, this would be a no, this would be a no, but this would be a yes. So, minus y. Okay. So, okay. No, that is not the same equation. So this is not symmetric with respect to the x. This has no symmetry. Okay. This looks like it's going to be symmetric with respect to all three because you're squaring these two squares. Yeah. So checking symmetry with respect to the x-axis, let's replace y with minus y. Okay, so it's symmetric it's the same equation, symmetric with respect to the x-axis. Let's check the y-axis. Okay. Yes. And now checking the origin. Yeah, so all three. Now this isn't a circle, I don't think. Let's graph this and see what it is. All right, this is a hyperbola. So you you come here. This is, we're at, well, let's do, any minus x comma y. Okay, multiply x by minus 1. You get x comma y, so you come to here. We're on the graph. So symmetric with respect to the y-axis. All right, let's come back. Multiply y by minus 1. We're on the graph. Okay, so we're symmetric with respect to the x and y, and so we're going to be symmetric with respect to the origin. If we multiplied x by minus 1. Now let's multiply y by minus 1. On the graph. See? Okay. Let's check. This is a line, right? Y is equal to mx plus b. So let's think about if we have a line, what do we expect this to be? So x is equal to 0, y is equal to minus 3. And then the slope is, okay, so go over 2, up 1. Over 2, up 1. I mean, to me, this is going to have no symmetry. I guess only horizontal and vertical lines would have a symmetry, and then maybe a line going through the origin, a 45-degree line, would have symmetry about the origin. Okay, so let's check symmetry about the x-axis. No. Symmetry about the y-axis. No. Symmetry about the x-axis. Or symmetry about the origin. Close, but no, because it's plus 3, not minus 3. But let's say we had, but just y is equal to x. That's a 45-degree line going through the origin. If you replace y with minus y and x with minus x, you get, see? So symmetry about the origin. You use the graph to determine if the function is even, odd, or neither. Okay, so we just studied just general equation symmetry. Any equation, function or not function, the idea of symmetry. Don't get this confused. It's, you get these new terms, even and odd. You think you're venturing into some new territory. You're not. All we're doing here, when we talk about function symmetry, you're just restricting to, now we're only dealing with functions. Functions are restricted. They only have, they don't have all forms of symmetry. They can't, because a function is restricted, right? You can't have a symmetry about the x-axis when it comes to a function, unless it's f of x is equal to 0, a horizontal line going through the x-axis. Other than that, you can't, because then it's not a function. In order to have symmetry, you have to have at least 2 values corresponding to the same x value. That's the whole idea. Symmetry about the x-axis is you multiply y by minus 1, and then you're still in the graph. The x hasn't changed. Well, that's not a function. Okay? So the only 2 forms of symmetry for a function are symmetry about the y-axis and about the origin. Because about the origin, we looked at an example here, or even the horizontal line going 45 degrees, that's a function, right? That passes the vertical line test. Okay? And these names, these are just names. A function that is symmetrical about the y-axis is called even. A function that's symmetrical about the origin is called odd. That's it. Okay, so let's look at this graphically. This is a function, right? It passes the vertical line test. Is this function even, odd, or neither? Okay, let's check symmetry about the y-axis. So we go from, looks like minus about 1.5 to 1.5. Okay, yeah. Well, okay, but let's go from here to here. No, right? If you go from here, this is about 1, 2, minus 2.5, 1, 2. So not symmetric with respect to the y-axis. What about the origin? So we go from here to here, okay, and then from here to here. All right, that worked. Let's go from here to here, and then from here to here. Yeah, it looks like it's symmetric about the origin. So this would be odd. Now let's think about, could a function be even and odd? Think about that on your own based on what you learned in the previous video and in this video. Think about that on your own and drop a comment. Okay. Looks like it could be even. What about odd? Go from here to here and then here to here. No. Well, yeah, okay, so we found one point that the odd wasn't satisfied, so it's not going to be odd. But we can check another point. Here to here. And then we're about 1, 2, 3.1 away. 1, 2, no. So this is even. Symmetric with respect to the y-axis. Okay, so let's go here to about here and then flip. No, so it's not odd. But then checking about the y-axis. Okay, we go from here to here, yeah. What about here? Here to here? Yeah, symmetric with respect to the y-axis. It's kind of weird to see that, but it is. Not the x-axis. That's not even possible for a function. Again, unless it's f of x is equal to 0. That's like a trivial case. But this is even. Okay. This doesn't look like it's going to be even or odd for sure. Because, yeah, I mean, look. It can't be even for sure. But maybe it's odd. So we go from plus 2, minus 2, and then we flip to right past 4. No, not even or odd. Neither. Okay, determine if the function is even, odd, or neither. Now, the next confusing part, the first thing that's confusing, in my opinion, is that you have these different names for symmetry of the functions. The symmetry of functions has these different sounding names, even and odd, compared to symmetry about the x and y axis. So you tend to, I felt like I tended to forget that with even and odd functions, it's just a name we're talking about dealing with symmetry of a graph about the x, y axis or origin. Okay, but then the next confusing part is that with a function, one way to look at it is through function notation. This idea of symmetry. So in other words, when we in the beginning of the video, we had like an equation, and this could be a function or whatever, and we were replacing y with minus y and x with minus x. And so, but how do we look at that with function notation? Okay, well, with a function in function notation, the idea is if it's even, meaning it's symmetric with respect to the y-axis, so you're replacing x with minus x, and and then you simplify and you get nothing changes. So what does that mean in function notation? That means this: f of minus x is equal to f of x, right? That's the idea. Okay, now for an odd function, it's a little bit harder to see how this would look in function notation, but what's the idea? The idea is, so if we had y is equal to x squared plus 6, we replace x with minus x, okay? All right, so that's f of minus x. All right, so, well, let me do this. Let's say, let me actually put an odd function. Okay, so you replace x with minus x. All right, so we do this, f of minus x. So that simplifies to this. Well, okay, hold on. That's not That's not an odd function, sorry, because I shifted it up. So, okay, here we go. This is an odd function. So you replace x with minus x. All right, f of minus x. Simplify. Okay, now we don't have the same equation back, so it's not an even function, but if we replace y with minus y, we do get the original equation back. So what does that mean? What's this going to be equal to? F of minus x. It's going to be equal to minus f of x. It's kind of confusing, but that's the idea. This all means the same thing. These two processes are the same thing. F of minus x, like, okay, this is f of minus x. Okay, what is minus f of x? It's the same thing, right? You replace the x with minus 1, and you get the same thing as if you replace the y with minus 1. It's like a roundabout way of looking at what odd symmetry is, but in function notation. It's kind of confusing. Okay, so is this function even, odd, or neither? Let's check if it's even. Just does f of minus x equal to f of x? So 3x to the 6 plus 2x squared plus, yes, this is even. Now checking for odd, this is f of minus x. Does that equal minus f of x? No. If we did put a minus sign in front of this, that would be different. So this is even. Okay, let's check for even. So minus 13x cubed minus 12x. No, but if we have this k of minus x equal to minus k of x, this is k of minus x. What's minus k of x? Yeah, so this is odd. Okay, let's check for even. Well, okay, let's do this. This is, we've got a squared, this is 4 squared, minus b squared. 4 squared minus x minus 3 squared. So that is, we can factor that as a plus b, 4 plus x minus 3, a minus b. So 4 minus x minus 3, which is 4 minus x plus 3. So this is 1 plus x, and then 7 minus x. So, okay. So now n of minus x is equal to 1 minus x, 7 plus x. Okay, so what is minus n of x? That's, I mean, neither, right? N of minus x does not equal to n of x, and n of minus x does not equal to minus n of x. Okay, let's check for even. 16 plus, okay, it is even. But minus q of x is just minus square root of 16 plus x squared. That's not the same thing. So this is even. Okay, h of minus x is minus 5x, which is not equal to h of x. Minus h of x is minus 5x, which is equal to h of minus x, so this is odd. Okay, f of minus x is, so okay, minus x minus 4 squared. So if I did x is equal to 3, I would get minus 3 minus 4 would be minus 7 squared. If I did x is equal to 3 here, I would get minus 1. Or no, I'd get 1 minus 4 minus 3. So no, this is not equal to f of x. What about minus f of x? This is kind of tricky because could I, if I did this, if I put a minus sign in front of, if we put a minus sign here, could we convert this? Like, in other words, can we convert this to this? And no, we can't. I would say we can't, just looking at it. So neither. Okay. Minus. Okay, so minus 1 to the 5th is minus 1, so you got x to the 5th. No, that is not equal to v of x. Okay, minus v of x is, and that is equal to v of minus x, so this is odd. See, this is v of minus x. Those two are equal. All right.